What happens when AI systems must remember, recover, and reason in worlds they've never fully seen? In this episode, we dive into three striking papers that push the boundaries of intelligent behavior: an agent that learns when to reflect and when to retrieve, a robot training method that turns simulated failures into scalable human-guided recovery, and a deep look at why transformers struggle with unseen symbols in symbolic reasoning. Together, they reveal how AI can improve, adapt, and generalize, and where it still breaks. Let's explore the first paper: AEL Agent Evolving Learning for Open-Ended Environments. AEL introduces a two-timescale self-improvement framework for open-ended LLM agents that targets the real bottleneck, not memory storage, but memory utilization under module interaction uncertainty. At the fast timescale, a Thompson sampling bandit selects among memory retrieval policies episode by episode. At the slow timescale, LLM-driven reflection diagnoses failure modes from aggregated trajectories and injects causal insights into the prompt, only evolving new retrieval policies when the current pool is inadequate. The default system keeps planner and tools fixed, uses a three-tier memory stack: episodic, semantic, procedural, and learns a retrieval policy over 5 initial memory modes, with retrieval scored by feature match, quality, recency, and tier-specific boosts. The key novelty is its diagnose before prescribe design, which treats the agent as a coupled system and explicitly studies multi-module credit assignment. On the default sequential portfolio benchmark with 10 sector-diverse tickers, 208 hourly episodes, and 5 seeds, AEL achieves a Sharp ratio of 2.13 plus or minus 0.47, outperforming 5 prior self-improving methods including reflection, expel, factor minor, meta-reflection, and evotool, as well as all non-LLM baselines. It also reaches Sortino 4.08 and Kalmar 10.4, with the lowest variance among LLM methods and max drawdown of minus 1.53%. Ablations show a strong less is more effect. Memory alone improves Sharp from 1.35 to 1.68, and reflection lifts it further to 2.13, a 58% cumulative gain over stateless behavior. By contrast, planner evolution, per tool selection, cold start priors, skill extraction, and sophisticated credit methods all degrade performance, with planner evolution and per tool selection dropping Sharp to 0.41 and 0.43. Uniform credit consistently beats FCC and LLM FCC, indicating that in short horizon, high noise environments, simpler online allocation outperforms elaborate attribution schemes. Let's explore the second paper: High WM Human in the World Model for Scalable Robot Post-Training. High WM, short for Human in the World Model, reframes robot post-training as human correction inside an action-conditioned world model rather than on the physical robot. A pre-trained policy is rolled out closed-loop in the learned simulator. When behavior becomes failure-prone, a human injects short corrective actions through a hardware-agnostic interface, and High WM caches states so the operator can roll back and branch multiple recovery continuations from the same pre-failure state. This converts one real failure into dense supervision around the policy's weakest regions. The world model is trained with a 1-4-dimensional continuous action space, includes failure, off-task trajectories, and edge case coverage to improve fidelity, and is used to collect corrective segments that are then added back into post-training. The paper evaluates the method on 3 real-world dual-arm manipulation tasks, spanning rigid and deformable objects: fold towel, push T, and root rope, using 2 policy backbones: DP and pi null. High WM achieves the best real-world success in all 6 task policy combinations, improving success by 37.9 percentage points over the base policy and by 19 points over a world model closed-loop baseline that only collects successful self-rollouts. World model task success correlates strongly with real-world success, with Pearson R equals 0.953, indicating the simulator is reliable enough for intervention and evaluation. With increasing virtual intervention data, performance improves monotonically, and at the largest scale, the method yields nearly $100,000 in cost savings by avoiding repeated robot deployment, resets, and hardware occupancy. The core novelty is using the world model not as a generator or evaluator alone, but as a reusable corrective substrate for scalable, failure-targeted robot post-training. Let's explore the third paper: To See the Unseen on the Generalization Ability of Transformers in Symbolic Reasoning. The paper shows that decoder-only transformers fail on in-context propositional logic reasoning with unseen symbols, not only because they cannot copy novel tokens, but because training drives the last layer token representations to collapse. In tied unembedding models, the unseen token unembeddings converge to nearly the same direction and magnitude, making distinct unseen variables nearly indistinguishable. The authors prove a contraction result for two regularized SGD, GD with bounded features. Once the model fits the training data and unseen class probabilities become small, the distance between two unseen label vectors shrinks by a factor tied to weight decay and softmax probabilities. Empirically, the same collapse appears under Atom W with layer norm. On synthetic Hornclaws datasets with up to 20 predicates and 40 rules per example, a 1-0, layer 60, 75 M parameter decoder-only transformer trained on 100 held-out tokens generalizes poorly when any variable is unseen. A copy attention modification helps on single unseen queries, but fails when all predicates are unseen unless combined with higher symbolic diversity, freezing embeddings, or periodic reinitialization. With frozen embeddings, unseen token reasoning succeeds because initial embeddings are approximately orthogonal. With active forgetting, generalization is restored only when collapse is prevented continuously or when copy attention supplies a sharp retrieval path. Temporary active forgetting alone does not sustain the inductive bias. The paper also reports collapse in open-weight Gemma 3 models. The 99 reserved unused tokens have mean cosine similarity 0.78, 0.33, 0.23, and 0.24 inches, the 1B, 4B, 12B, and 27B models, versus 0.09, 0.03, 0.02, and 0.01 for used tokens. Fine-tuning Gemma 3.1b on logic with unused tokens is about 10 times slower to reach 90% accuracy than using ordinary adjectives or letters. That's a wrap on today's AI paper highlights. Thanks for watching.